Hey there. Looks like, sorry for the late start. Had a little bit of technical problems. It looks like you're going to have a private lecture there in chapter 16. How are you doing today? Doing okay? Doing good. Doing good. Um, we're going to do chapter 16. I'll knock that out. But basically, it's not going to be on the final, but there is homework on it. You know, you're more than welcome. I can talk about it, or you can just read it on your own, whichever one you feel comfortable with. I'll give you that option, since you're the only one here. Yeah. I'm gonna go ahead and just talk about it. It's a very short, okay, very short chapter. All right. So we'll see if anyone else shows up. Okay, well, this deals with gases. Okay. Now, pressure is defined as the force per unit area, usually at 1 square cubic meter, 1 square cubic centimeter. And that is the amount of molecules that are pushing up against the walls of whatever container it's in. So it's force per unit area, okay? That's how we define pressure. Now, we can increase the pressure of a gas by increasing the number of collisions up against the wall, okay? And so we can, okay, no problem. I hear you got background noise. Okay, well, let me just go with this. All right, so we can do one thing. The pressure, if we increase the number of collisions, meaning that we can heat it up, add more atoms into the container, our pressure goes up, okay? So, pardon me 1 second. Okay, so we can increase the number of collisions by either increasing the temperature or increasing the number of atoms inside the container, which causes the pressure to increase. Temperature is a good indicator. Like in the morning, you drive your vehicle, you get out to your vehicle, the tires are whatever temperature they're at, and let's say you drive on a highway for an hour. Well, it picks up heat from the friction. If you were to measure the temperature, you'll find it that measure the pressure, you'll find that the pressure would have increased after that 1 hour, just simply because of the pressure. All right. And obviously, if you go to a quick trip, you add more air into your tire, obviously the pressure goes up because you're putting more matter into the container. Now, in a vacuum, there is no pressure. Okay. Now, with respect to atmospheric pressure, that is the force that is hitting on us, all around us. Now, there's a lot of force out here, you know. And if you do a quick calculation, you're gonna be like, whoa, that's a lot of pressure. For example, let's take let's assume that this is like 1 square meter, okay? So we got 1 meter by 1 meter, and then we go up from where you're at right now, all the way up to, you know, bear with me for 1 second. I got a call I've been waiting for, and I got to answer it. Sorry, I needed to answer that. So let's say you're right where you're at right now. So you measure 1 meter by 1 meter around you, and then you measure 10 meters up in the up direction, okay? And so what you have here is 10,000 cubic meters, right? In that area, in that little 1 meter by 1 meter by 10,000 meters up in the air. Now, if you look at the density of air, you'll find it to be average about 1.225 kilograms per cubic meter, all right? Now, if I take that and I multiply that by the cubic meters that you're sitting in, that's 10,000 cubic meters. The weight of the air that's hitting on you is about, check my math, 12,250 kilograms. You imagine that? That's how much weight's on you right now. That's about 100 and that's about, check my numbers, but that's about 127 pounds of air that are hitting on you. Obviously, there's a variation because obviously as you go up higher, there's not that much air in there. But that gives you an idea of, how much air that's hitting on you. And you wonder, oh my goodness, well, how come if that much air is hitting on me, how come I don't collapse? Well, the reason you don't collapse is because internally, the way we've adapted to this atmosphere out here is we put a counter pressure. For every pressure, there's a counter pressure of equal amount. Okay, one of the laws of physics. So internally, we're outputting the counter pressure to counter the pressure that's being hit on us by externally. And that's why, for example, animals that survive down under the sea, a couple 5,000 feet under the sea or so, there's a whole ecosystem down there, and if we went down there, we'd crush like a tin can because we don't have the counter pressure to counter the excessive pressure that's being hit on us. Whereas those animals down there do, that's the way they adapted. If we were to bring them up, they would have a problem up here in atmospheric pressure. But that's a lot of air or a lot of weight that's on you, which we don't really even think about, okay? Now, as you climb up go up higher, there's less air, simply because there's just less air, okay? Now, with respect to units of pressure, the way that works is we have what's called a barometer. Now, a barometer is simply basically it's a tube, an inverted tube. You can see the picture of it here, and where you have atmospheric pressure being pressed on the liquid. Now, as the atmospheric pressure goes up and down, depending on the climate and what's going on, this mercury, most of the time this is mercury inside, okay, will go up and down. And we have a scale here that we can put, all right? And it's a scale that we can then measure the atmospheric pressure. Now, 1 atmosphere is set up at 760 millimeters of mercury. So 1 atmosphere, which is our standard reference point, is equal to 760 millimeters of mercury, as is shown here. It is also equal to another unit called torr. It's also equal to 760 torr units. And if we want to go into convert into English units, that is equivalent to 14.7 pounds per square inch, PSI. Okay. Now we use mercury because mercury is obviously a liquid metal. It's very dense. You can use any type of liquid to create a barometer. However, if we were to use water, because the density of water, we would require a meter. A barometer is about 32 feet long, simply because the density of the water is much, much less than the density of mercury. So anyway, that's how we measure pressure, okay, using a barometer. Now, with that, and there's our conversion factors. 1 atmosphere is equal to 760 torr, or it's equal to 760 millimeters of mercury, or 14.7 psi. Those are ratios. And like we've been dealing with conversion factors, those are ratios that we can utilize. So if you ever have a problem, it says, one needs you to convert 44 PSI, pounds per square inch. We need to convert that to torr, to atmosphere, and to mercury. We utilize the conversion factors in the previous page. We know that 1 atmosphere is 14.7. We set it up like we've done in any other problem in a manner such that our units cancel out. So we set up 1 atmosphere in a numerator for the first problem to get us into atmosphere. And we start off with pounds per square inch, and PSI must be in the bottom. So we take 4,400 divided by 14.7, and we end up with 3.0 times 10 to the second atmosphere. Okay. We start off with PSI. We need to get to torr. All right. Well, we got that conversion factor that 760 torr is equal to 14.7 PSI. And we put the PSI in the denominator because we want that unit to cancel, giving us the units of torr. So 4,400 torr or PSI is equal to 230,000 for pressure units. And then since we know that 760 torr is equal to 760 millimeters of mercury, to get to torr to mercury, it's a 1-to-1, okay? So 230 torr is equal to 230,000 millimeters of mercury. Okay, so those are examples of conversion factors of units of pressure for gases. Okay, now we're going to determine some relationships here because that's going to help us set up some equations that we're going to utilize. And this here is quite intuitive if you really stop and think about this for a moment, okay? Now, if the volume increases, the pressure, think about this for a second. All right, let's think about it in terms of your tire in your vehicle. You have a tire of an X amount of diameters in volume, okay? You've got enough air in there at let's call it 32 PSI, okay? Of pressure, pounds per square inch of pressure, and everything's good, right? Now, what if you were to take that amount of matter of gas molecules that's in your car tire, and then you put all that into a tire that belongs to an 18-wheeler, okay? Big old giant tire. What do you think the pressure happens? The pressure would be less, right? Okay, the volume increase of the pressure dropped. Okay, so as the volume increases of the container, the pressure drops. Now, with respect to temperature, as I stated earlier, you get up in the morning, you get in your vehicle, your tires are set at 32 PSI. You drive for a good hour drive on the highway, going the speed limit, obviously, right? Okay, you stop, you check the tires, they're warm. You can touch them, they're warm because of the friction involved, okay? And if you were to check the pressure, you'll find it to be greater than 32 PSI. So that means that as the temperature increases, our pressure increases, okay? Quite intuitive, right? Makes sense. Now, if the number of gas atoms increase, guess what? The pressure goes up. If your tire is at 30 PSI and you go to Circle K to put some air in there, what are you doing? You're putting air into the tire. You're putting more gas atoms into the tire. You increase the number of the atoms banging up against the tire, the inside of the tire, the pressure goes up, okay? The pressure goes up. And it brings us to a description of the relationship of these variables. We're going to have 3 variables that we're going to work with, okay? We're going to have volume variable, we're going to have pressure, and we're going to have temperature with respect to gases, okay? Those are the 3 variables we're going to deal with. with respect to the gas atoms, that we're going to hold that constant. We're going to say we're going to add an X amount of volume of gas atoms in the container, and we're going to do some measurements. Now we got three variables. Okay. Now we just noticed in number one that when the volume increases, guess what? The pressure decreases. We call that an indirect relationship. Okay. Indirect relationship. As one variable goes up, the other variable that's tied into it goes down. Okay. We also see that as the pressure, with the relationship between pressure and temperature, number two, as we increase the pressure, guess what? As we increase the temperature, the pressure went up. That is a direct relationship. Okay. A direct relationship. And the same is true with the number of atoms, meaning that as we increase the number of atoms, the pressure increased. The variables, both variables increase one variable, the other variable increase proportionally. So that also is a direct relationship. Okay. So what we can do is let's take the first relationship, in that when the volume increase, the temperature, the pressure decreased. Okay, so that is an indirect relationship. So we can write an equation to describe that relationship, meaning that the volume is equal to 1 over the pressure, because the pressure decreases, an indirect relationship. Once we have a relationship, we can write in an equation. Guess what? We can actually take this equation we just wrote and assign to it a constant. Okay. And we have actually created an equation here that relates volume and pressure while we keep temperature constant. And so we can set up a bunch of experiments where we keep the temperature at whatever temperature you want to keep it at. Let's just say 50 degrees Celsius. Okay. And we play with the volume and the pressure. And so we have an X amount of volume. We measure the pressure. Change the volume, measure the pressure again. Change the volume again, measure the pressure. We get a multiple of data points. Well, what happens is with that, this K is a constant. It never changes. Okay, we can rearrange this equation and say VP is equal to K. And so when we change the volume, pressure changes proportionally, because that's a constant. K is a constant. And we have the product of the new volume and the product of the new pressure would be constant. So we can have two relationships here, meaning that V1, we start with the initial, we start with an initial measurement of volume and pressure, okay? And that's going to be equal to some constant, okay? And then we change the volume to a different parameter, okay? Different value. What that means that pressure is going to change accordingly. So we have a second set of conditions. That K in both cases is going to be the same. It's a constant. And when K is a constant, guess what? We can equate these two equations with each other. We can say that V1 times P1 is equal to V2 times P2. Okay, we have this relationship. So now we can predict either the volume or the pressure in two sets of different conditions. If we know three of these variables, V1, V2, there's four variables here, V1, P1, V2, and P2. We can now play with three of those variables and calculate what the fourth one is. We have four equations, four variables, four unknowns, right? If we know three of them, we can calculate what the fourth one is. And that brings forward this relationship here. Let me clear my mess up a little bit. And that's where Charles Boyle, he did a lot of work with respect to gases while holding the temperature constant. Okay, temperature is constant, is equal to constant temperature here, whatever that may be. And he found this relationship where the subscript 1 indicates the initial conditions of pressure and volume, and the subscript 2 indicates the final conditions of pressure and volume. And so you're always going to know three of those variables so you can calculate the fourth variable. Okay, and here they, like I said, at constant temperature. All right, now Charles' law, what he did here is go through the same analysis we just did, okay, because we know that the difference here, notice there's no P here, so pressure is held constant. And so he put some gas in a constant pressure, 1 atmosphere, whatever you want to heat, whatever he set it up to. And then he played with the volume and the temperature. And he found this relationship, that the ratio of the initial volume and the temperature is equal to the ratio of the final volume and the final temperature. Okay, so that's what Charles' law is all about. Then you have Boyles law. Guess what? Volume in this case is constant. And so these two scientists took a known volume and held it constant, and then played with the pressure and the temperature. Okay, and they found out that the ratio of the pressure and temperature of the initial conditions is equal to the ratio of the pressure and temperature of the final conditions. Okay, so you have three different laws and equations that came about by holding one of the three variables: temperature, pressure, or volume. Now, the cool thing about this is that we can combine these three laws, Boyles Law, Charles' Law, and Boyles Law, and come up with this relationship where you got P1 times V1 divided by T1, okay, is equal to the second set of conditions of pressure times volume divided by the second temperature, okay? And so when you have word problems that do not mention, let's say you have a word problem asking you to calculate your pressure and volume, and there's no mention of temperature, okay? Because temperature is held constant, you just utilize Boyles Law. When you have a problem and there's no mention, or they tell you pressure is held constant, you use Charles' Law. And with the volume is constant, you use Boyles Law, okay? Now, you will find that all these here, you know, if volume is held constant, you'll find if you're solving for, say, P2, guess what? If volume has the same value, let's say volume is 100 and the second volume is 100, and once I move that volume 2 over here at 100, and that's T2 over here, hey, they cancel out. You know, 100 divided by 100, they cancel out. Okay, so you either remember to use each one of the three laws, or you can use the combined gas law and remember that the variable that they don't mention will cancel out. Okay. All right. And so, for example, we can do gas law calculations. Now, the thing is that you have to remember is that, one, temperature for all of these calculations were determined in Kelvin. Okay. the volume has to be equal on both sides. Whatever volume units you're using, liters, milliliters, whatever, if you use it, you're welcome to use any of them as long on both sides of the equation that they are the same, because you're going to cancel. Pressure units have to be the same on both sides, okay? So they can cancel out accordingly. And identifying from the word problem the initial conditions, which would be the subscript 1, and then identify the final conditions, which would be noted by subscript 2. Okay? Now, if any of the variables, pressure, volume, or temperature, are not mentioned in the problem, or they are mentioned, but there's no change in them, then, they cancel out automatically, okay? So you just simply plug and solve the problems and keep tracking your units and obviously your sig fix. For example, a sample of carbon dioxide gas occupies 2.25 liters at 758 torr. Find the final volume if the pressure is decreased to 698. All right, so I can do this. I can go this route. Oh, this is one here. P2, V2 over E2. Okay. Okay, the sample of carbon dioxide occupies 2.25 liters and 258 torr pressure. Find the final volume. So guess what? Final volume would be this. That is what we're looking for. Okay. They're telling us the initial volume is 2.25 liters and the pressure is 758 torr. Okay. And if the second volume is decreased to 698 torr, okay, you can see that the temperatures are not mentioned here, so we can cancel those guys out. And so now we have 758 times 2.25 liters. I don't want to divide that by 698 torr is equal to my volume. That's what we're looking for. Okay, notice that torrs cancel. Plug in the numbers and you have your answer. Okay, here, let me clear this up a little bit. Then there's the equation, because there's no mention of temperature here. All right, plug in the numbers, and now your volume is 2.44 liters. Okay. All right, a sample of krypton gas occupies 3.91 liters at 105 degrees Celsius. Find the final temperature in Celsius of the gas if the volume is changed to 6.05 liters. All right. And so here we're holding pressure is being held constant. And so at constant pressure, we do a measurement, and that krypton gas has an initial volume of 3.91 liters, and it is held at 105 degrees Celsius. Okay. And we want to calculate the final temperature if we change the volume to 6.05 liters. Now remember, temperature must be in Kelvin, so in the calculations. The problem says to find the temperature in Celsius, so you're going to do the calculations in Kelvin. Your answer will be in Kelvin, but then you're going to subtract the 273 to put it back into Celsius. Remember that. So plug it into the equations, you end up with 585 Kelvin temperature-wise, which is equivalent to 312 degrees Celsius. All right, A steel container filled with nitrous oxide at 15 atmospheres is cooled from, oh, did I forget something here? Yes, yes. Remember, no, okay. Remember we did STP, standard temperature and pressure? Well, we'll get to that here in a second. 0 degrees in 1 atmosphere. All right. So a steel container is filled with the gas, nitrous oxide. It is at 15 atmospheres and is cooled from 25.5 degrees to a negative 40.8 degrees. Find the final pressure, okay? And so here we got a volume which is constant. It's a steel container, whatever the volume would be. So volume is not involved here. All we're going to work with is pressure and temperature, okay? And so P2 is the ratio of P times T2 divided by T1. So I rearrange that P1 over T1 equation and solve for P2 because that is what we're looking for, and then plug in the numbers. Okay, and then if you think about it, that does make sense that the pressure drops. What have you done here? You got a steel container of gas, and you went from essentially room temperature, 25.5 degrees Celsius, and you dropped it down to negative 40. You know, dropped it, made it very cold. Well, what's happening here? If you think about it, the gas molecules, now you have removed energy from the gas molecules and they start to condense, okay? So there's less gas molecules pounding up against the walls of the steel container, and hence the pressure drops, okay? And now it went from 15 atmospheres of pressure to 11.7 atmospheres of pressure. So it basically dropped pretty about four atmospheres of pressure. Remember, we are 1 atmosphere, so about dropped it by 4 atmospheres. So that's a lot of pressure. Okay. Recall we had talked about STP, standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere are standard temperature and pressure. And so here, guess what they're telling you here? We have a nitrogen gas sample. It occupies 50.5 milliliters at negative 82.8 degrees Celsius and has a pressure of 1250 torr. It wants to know what is the volume of this material, nitrogen gas, at standard temperature and pressure. And so here we can utilize the combined gas law because we're given all the variables that we need. We're given V1 right there. We're given T1 right there, and we're given P1 right there. Standard temperature and pressure is 0 degrees and 1 atmosphere. Okay, and so now we're given T2 and P2, and we're looking for V2 is what we're looking for. All right, keep in mind the units. We got atmosphere here, but we got torr over here. Your choice is to either convert to atmosphere or to convert to torr. Whatever the case may be, doesn't make any difference, just as long as the units are the same on both sides of the equation. So we're gonna deal with the temperature, but that's our first couple of slides. They gave you that relationship between atmosphere and torr. You can convert one to the other. Then all calculations have to be in Kelvin. So we're gonna convert Celsius to Kelvin, okay? So those are the things you have to be aware of when you are doing these calculations. So you plug and play. So you got 1250 torr, 50 point, the volume we can keep the same, okay? We can keep it at what it is, milliliters, or we can convert that 50.5 milliliters to liters, whatever you want to use, that's fine. Okay? Just keeping the same. So we have, then the temperature 0 degrees is 273 K, all right? And they just plug the numbers in, and now your volume, okay, is 119 milliliters. Now, does that number make sense? So think about this for a second, okay? You start off at negative 82.8 degrees Celsius. And by doing that, you change your new temperature to 0 degrees. And so what are you doing? You're down at negative 82 and you're heating it up. So doesn't it make sense that your volume would go up? Okay? Because you start off at 50.5 milliliters and your final volume now it is at 119, which is consistent with what you're doing physically, okay? And that's what I mean by, I've stated before, when you do the calculations, you look at that number and ask yourself the question, does that number make sense based on the mathematical function of what I'm doing, or based on what I'm doing to it physically? At least in this case, what am I doing to the gas? I'm heating it up, okay? All right, so up to this point, these equations, all these equations deal with going from one set of conditions, be it pressure, volume, or temperature, okay, which is the subscript 1, going from that set of conditions to a second set of conditions going to subscript 2, okay, being pressure, volume, temperature. That's what these calculations or these equations deal with. This equation here is called the ideal gas law, okay? Earlier, we had talked about the gases had no volume, but we couldn't do much about it, okay? And I said at the time, well, only in certain conditions at STP, we know that 1 mole of gas occupied a volume of 22.4 liters, okay? So I started out with kind of fudging the truth a little bit and say, in the beginning, yeah, gases, we can't measure the volume. And then I said, okay, now only at STP, we know that 1 mole occupies 22.4 liters of gas, any gas. Now I'm gonna go to the full truth. That if we know, we can use the ideal gas law to calculate pressure, volume, or we can even calculate moles, and we can calculate temperature. Our 3 variables, P, V, N, and T. R is a constant, and we'll define that, okay? Well, to use this equation, we use pressure, but those units must be in atmosphere. The reason these units have to be in certain, the reason these variables have to be in certain units has to do with R. R is a constant, and the constant you use, which that constant could use a variety of different units, but the ones we're going to use have specific units that you have to use. So volume is in liters, okay? N represents the number of moles of a gas. And R is the constant. In this case, it is 0.08206. Note the units, liters, atmosphere, per mole Kelvin, okay? And hence, that's why for pressure must be in atmosphere, and volume is in liters, and obviously moles is moles, okay? And temperature has to be in Kelvin. And it's because of the constant that we utilize, which is defined. We can use a different constant with different units, and we have to change the other variables accordingly. Okay, but to keep it simple, use R as 0.08206 liters atmosphere per mole Kelvin. And you shouldn't have any problems. All right. So, and of course, temperature is Kelvin. And so now we have 4 variables: pressure, volume, the number of moles, and temperature. R is constant, it never changes, okay? And so having 4 variables, 4 unknowns, you could be given 3 of those unknowns to calculate the 4th unknown, okay? And keep in mind, once we know the moles, we can go from moles to grams. If we've done before, right? And multiplying by the molar mass. Or if we got grams of some gas and we need to calculate moles, we divide by the molar mass. Okay, so the combined gas law, as I stated, is what in the equation we use. We have changing conditions, where the ideal gas law is dealing with initial conditions. There's no change in condition here. Telling you, here's the pressure, here's the volume, here's the moles, here's the temperature. Calculate one or the other, one of those variables. For example, what is the volume of a gas if the pressure is 3.56 atmosphere, the temperature is 25.6 degrees Celsius, and there are 33.35 grams of carbon monoxide present, okay? And so here, the ideal gas law is PV is equal to nRT. Question says we want volume, so then we arrange the equation to say volume is equal to, excuse me, that's nRT divided by pressure. That is the equation that we're going to utilize, okay? So we need to know the number of moles. We got 3.35 grams of moles. That means that we need the molar mass of carbon monoxide. So we got 16 and 12, so you got 28.01, 28.01 grams per mole, molar mass, okay? We need this temperature to Kelvin, so we're gonna add 273 K to that, all right? And atmosphere was good, okay? We're gonna do some additional calculations and change to 25.6 to Kelvin. It's 298.6 Kelvin. Pressure is fine at 3.56 atmosphere. We need to convert 33.35 grams of carbon monoxide to moles. Okay, I wouldn't truncate anything here, so you can see that long number of 1.190646. Okay. That's the number of moles of carbon monoxide. And now we just plug in the numbers. All right. And we solve for volume. And so at the volume, we have 8.20 liters. So at 25.6 degrees Celsius and at 3.56 atmospheres of pressure, okay, 33.35 grams of carbon monoxide would have a volume of 8.20 liters. Okay. All right. In fact, you can use the ideal gas law equation to actually calculate 1 mole of gas at FCP, and you'll see it to be 22.4 liters. All right, this pretty much says, this is just additional information dealing with gases out there. There was a publication when I was in graduate school that this is back in the 80s. They were studying emission of gases coming from cows. And they were at that time, 30 plus years ago, stating that we're going to have a potential problem. Well, we're kind of here there. We're here, but I'll give you the numbers. You calculate, make your own conclusion. Okay. Now, conservatively, you know, cows, as we know, and not just talking about cows, but there's a variety of different animals and humans, you know, can emit about 10 liters of a variety of gases in the air. Okay. So let's conservatively just say, all right, one cow, 10 liters of gas per hour. Yeah, that's a pretty good example, a pretty good guess, or being conservative. Well, okay, there's 24 hours at 364. So in a year, you're looking at 87,600 liters of gas per year per cow. Well, I don't know. There's ballpark 19 billion cows in the world. That is a lot of gas going into the atmosphere just from the bovines. You know, it's quadrillion. That's 1.6 quadrillion liters of gas that goes out there. And these numbers here give you an idea of how much material out there. But, and that's just one example here. At that time, when we read that publication, because I was in graduate school and we needed to bring publications to present in a particular class, we were all, you know, kind of joking about it and so forth. We didn't really understand the ramifications of it. And I'm thinking now, yeah, we're here now. We're here. There's a lot of material out there, because once it gets out there, it just doesn't disappear. Gravity keeps it here. And we have to find ways to either minimize it or to remove it from the atmosphere, because it will cause problems. Anyway, food for thought there. So with that being said, congratulations. You have completed 16 chapters of chemistry. Next week, I will be here. It's a study day, okay? I'll be in class. I'm in Zooms here if you have any questions. So come with any questions, because we are, let me see, our last day is our final, which is the 17th. Next week, we have exam number 5, okay, which covers the last 3 chapters. As I stated, chapter 16 won't be in that exam, nor will it be in the final exam, but there is homework, you know, for chapter 16. And on the 17th is the last day that anything can be turned in. And so if you have assignments you haven't completed, they're still open. Activity, assignments, those homeworks and such can be turned in, okay? There will be a penalty there, obviously, but they can be turned in. So do turn them in if you've not done them, because some points is better than no points. Don't forget about the nomenclature exam. You have an unlimited attempts, okay, until the 17th, and then that shuts down. But you got to have at least an 80% as per SCC departmental policy to get a passing grade. So it sets up, if you don't get the 80%, it drops back to 0. And it can have a factor on your grade depending on where you're at. If you're on the border, to boost you up to the next grade, it can kick you up to that grade, okay? Or if you're on the lower end of the border, it can kick you off a C and dump you into the D. So, you know, take that exam, you know, quite seriously and try to get that 80%, especially if you're in that borderline. If you're happy with where you're at, you're in the middle someplace, obviously it's going to have no effect on your overall grade. So, you know, that's your decision. All right. Any questions?